This video is second part of momentum principle and flow analysis. In the last video, we have found that force exerted by the fluid is F equal to m dot V2 minus V1. This is final velocity exiting the pipe or steam tube, and V1 is initial velocity entering the steam tube. Now in this video, we will study this force exerted by the fluid in two-dimensional system. This is for one-dimensional system. For two-dimensional system, we consider the inclined tube or bending tube. Here, I consider here tube of this type. The fluid enters with the velocity v1, making an angle theta1 with the horizontal. And similarly, fluid exit from this pipe, making angle theta2 with the horizontal. This is v2. Here, I write this language what is shown in the figure. You can write the figure name here, flow analysis. Here, fluid enters and exit that I have written here. Now, we can resolve this velocity in x direction and y direction. Suppose we assume here this x direction is positive in upward, vertical axis, y direction upward is positive. So that now we can find here or resolve here. This is theta1, so here is v1 cos theta. This v1 projection here. This vertical projection is v1 sin theta1. Similarly, here we can do this v2 is exiting outside, so here is v2 cos theta. Horizontal projection is cos theta, vertical projection is sin theta. So here is v2 sin theta 2. Here is theta 2. Here is theta 1. Now we can use this formula. We derived this formula in the previous video. This is second part of momentum principle and flow analysis. So we use this formula. This formula is derived from Newton's law. Net force is equal to rate of change of mass into change in velocity. This final velocity minus initial velocity. So we use this here. Net force is let Fx is the net force in x direction. We assume positive. Here sign convention also. And this is equal to rate of change of momentum. This is Newton's second law or momentum principle equation. This is x direction, and momentum principle is here m dot v2 minus v1. This rate of or mass flow rate or change in mass, rate of change of mass. Into this velocity, change in velocity. So that rate of change of mass means m dot into change in velocity. Here in x direction, we have your velocity v2 cos theta 2 and initial velocity v1 cos theta 1. So your final velocity v2 cos theta 2 minus initial velocity v1 cos theta 1. Or we can write this as a m dot into v2 cos theta 2 is the velocity in x direction. So it is v2 x minus this is v1 x. These are in x direction, so in suffix we write x. For exit v in suffix v2x and for entering v1 suffix x. Similarly, we can calculate the force on the vertical direction, net force on the vertical direction. Y direction. Let this is FOY equal to m dot the change in mass into the change in velocity in y direction. Finally, we have v2 sin theta 2 in upward direction positive minus initial velocity here v1 sin theta 1. This is equal to, in place of v2 sin theta 2 we can write like this v2y and this is v1y. We found here net force in x direction and net force in y direction. So we can find a resultant. Let resultant make angle alpha with the horizontal. So that resultant force is F of r. F of r is root under this f of x square plus f of y square. We use here triangle law of vector to find this f of r equals to f of x square plus f of y square. Or we can assume this is side as fx and this side as f of y. So that using Pythagoras theorem we can calculate this. And what is this angle? Alpha is the, if this is alpha, is perpendicular to the base, tan theta, tan alpha equal to f of y upon f of x. This implies alpha is tan inverse f of y upon f of x. This is the required value of angle that the resultant force made with the horizontal. In conclusion of first part this and second part this, we can say that net force is rho q, or here we can write m dot into v out velocity exiting from the steam tube or pipe or vents minus v in entering velocity, and this force is always in the direction of velocity. This is the force exerted by the fluid on this bend, and net reaction force is R, is always in the opposite direction, that we can write f of R minus in negative. Reaction force is always in the opposite direction. So in other video, next video, we will do the numerical related to momentum principle using this concept. First part plus second part. These two concepts are sufficient to do the numerical for momentum principle and flow analysis. Yeah.